Next in this unit is the study calorimetry, which is just determining the specific heat capacity of a substance. All right. All the, whether it's an indirect or direct method, okay, is based on this idea that energy is conserved. Right. This is the first law of thermodynamics. So effectively, what we have here is we have some test substance. All right. We'll say it is this little sphere right here. We don't know what its specific heat capacity is. So what we're supposed to be able to do, okay, is we're supposed to be able to put some water in it, all right, inside of one of these steel tubes, okay, and actually, sorry, the water comes to about here, actually, right there, okay. So we put water inside of one of these steel tubes, all right, these canisters, and we measure the temperature change of that water, all right. So we know what the temperature of the water is, we know what the mass of the water is, we know what the specific heat capacity of the water is. We know what the mass of the substance is that we're testing, and we know what its temperature change will be because we'll know its initial temperature and the temperature it ends up at thermal equilibrium with the water. So what we end up with here is being able to solve for the specific heat capacity of the unknown substance. So let me rephrase that here with some equations. The idea is that we have a cold substance, all right, that's going to be gaining some heat. Gaining some heat, and we have a warmer substance that will be losing heat, okay? And this is basically how I've written this out here. So what we end up with here is seeing, right, this kind of inequality, right? And we know all these variables except for the specific heat capacity of our unknown substance. Now what we can do is we can take this little pellet of whatever it is, okay, unobtainium we'll call it, and we can put it inside some boiling water, and we can get it up to the temperature of the boiling water. So we know what its starting temperature is. We know what its final temperature is because both the water inside the calorimeter and it will achieve thermal equilibrium, which means that after a while they'll both get the same temperature, okay? We can measure their masses and we know the specific capacity of water, therefore leaving us with this final piece to measure right here, okay? So that is the big idea with calorimetry. We have a couple different ways we can do it. Right here, what are we assuming? Well, we're assuming no thermal energy is lost to the environment, the container or the thermometer, okay? No thermal energy, so there we go, to the environment, the container, the stir even, okay, and the thermometer. Now, of course, this is unrealistic, okay? And we actually do account for these things when we do the calculations otherwise, but here we're just assuming that we can ignore it, okay? So let's do a quick example of this, or at least go through an example, okay? So we have a sample of metal, okay? It is heated to 100 degrees Celsius by placing it in boiling water for a few minutes. Then it's quickly transferred to a calorimeter containing this much water at that temperature. So after a while, thermal equilibrium is reached and the temperature of the water is 15 degrees Celsius. So we start out with this equation, all right, that I had from before, all right, which is this. Right? And what are we solving for? Well, we know the mass of the water is 0.40 kilograms. Okay, so basically what we're going to end up doing here is just, listing all of the knowns. So we know what this is, that's the mass of the water. We know the specific heat capacity of water, we can look at that up in the table. We know the change in temperature of the water, all right? It's going to go from 10 degrees Celsius to 15 degrees Celsius, is positive 5. We know the mass of the substance, 0.10 kilograms. We're looking for this. And we know that the temperature change will be negative 85 degrees Celsius, okay? When you plug in all those numbers, which I suggest you do and test it out, okay, the specific heat capacity of our substance is going to be equal to 985 joules per kilogram per degree Celsius. Okay, so we're checking on those numbers, but it should be around there. I guess that rounds to 1,000 with a sig figs. So then the question is, what is the thermal capacity of the metal sample? Since it's 0.10 kilograms, remember, okay, and actually, sorry, that's right there. The thermal capacity just going to be equal to the mass of the substance times the specific heat capacity. When you do this, you end up with 98.5 joules per degree Celsius. Okay. So that's a quick calorimetry example. Number 2 there, okay, gives you, tells you what the substance is, okay, and tells you that you also have to include the cup. So there's a little bit more balancing that's going to go on with that problem. And tell you what, I will help you to set that problem up, but I would love it if you solve for the final temperature of the water, or at least got there, okay? But the idea here, again, is delta Q of the cold substances, all right, is going to be equal to the heat lost from the hot substances. And so the only hot substance we have here is a block of copper that's being transferred in. So what we have to consider is delta Q of the water plus delta Q of the calorimeter, okay, is equal to negative delta Q of our sample. And all of these delta Qs are MCATs with different variables for all of them, but see if you can't get the final temperature, okay, of the water, which is 28.3 degrees Celsius. Go for it. You have all specific heat capacities in your notes there, okay? So yeah, that's it for calorimetry, and we'll do some more practice with that in class on Wednesday.